yesterday, we talked about ionic bonding, bonding between ions. And the thing about ionic bonding is that you have to, let's see, if we have H, no, let's not use H, never mind. Let's say we're sodium and fluorine. I'm sorry, what? Yes, it is. So here's the thing, folks. What we learned yesterday was that atoms like sodium have one outer electron, and they are perfectly happy to give up those electrons to fluorine, which has 7 outer electrons, and when it does so, it is able to be happy. Everybody's able to be happy because sodium then has its full octet of electrons in the 2s level underneath. Fluorine now has a filled 2s and 2p, 2s, 2p, 2s, 2p. Full octet, everybody's happy. It isn't giving the electron. Fluorine is taking the electron. One of the trends on the periodic table, which you're being tested on Friday, was called electronegativity. Who's willing to take a crack at telling me what that means? Yeah, it's okay.
It's like the strength they have to take the other electrons.
Right. It's the ability to take electrons. So the pull of the nucleus of one atom for the electrons of another atom, electronegativity. And what I didn't talk about really before was that the elements on the periodic table that form ionic compounds are very electronegative. Fluorine is the most electronegative. There's a scale of electronegativity, and it goes from the lowest one, well, the highest one is fluorine with a 4.0. And, you know, these are somewhere around, I don't know, 1 point something, I don't know what. And the way it works is that if two elements have a difference in electronegativity that's big enough, it's sort of like, you know, tug of war. You can have a stronger pull, but if you have elements that don't have a big enough difference in electronegativity, they can't take each other's electrons, and that's what I'm really going to talk about in a minute. Fluorine and sodium have a huge difference. Francium, or francium, as the English would say, francium. Actually, they would say like that. That would be, I don't know who would say that, but francium. Francium is a 0.9. It's the least electronegative, and so it gives up electrons incredibly easy to more electronegative elements. But let us look at a different example. Like, let's say hydrogen, which is also a group 1 element. It has 1 electron, and it would like to have either 2 electrons or no electrons. Remember, that will suffice for getting a full outer shell. And let's say a different player, oxygen. Oxygen is, I'm going to draw a little line here so we don't get confused by all these atoms here. Oh, okay. So oxygen is S2P4, which means it has this and this and this and this. And so how many does oxygen need? Right. What? 2. Right. Now maybe you meant one more after this one. So yeah, one of the problems is that we actually need to have 2 hydrogens, right? But that's not the only problem. So alright, so here we have 2 hydrogens. So oxygen takes hydrogen's electrons and everybody's happy. We have a nice ionic compound, right? Wrong. No. Because the electronegativity of oxygen is still relatively high at something like 3.3 3.4, maybe it's 3.7, I don't know. What do I look like? A chart of electronegativities? No. But the thing is, that would work perfectly well if this were sodium, or if this were francium, or something else. But it's not. It's hydrogen, which has an electronegativity of about 2.4. And it's just not enough of a difference. I think you have to have a difference. Some people say 1.7, some people say 2. It has to be a big difference. What? Okay? The difference just isn't enough. And so oxygen can try, it can sort of try to pull that electron, but it just can't do it. And so think of it as a tug of war. If this element isn't electronegative enough, it just can't pull that electron away. And so, does anybody know what actually happens instead? They share them. That is correct. They will share them in what's called a covalent bond. So this is the other kind of bonding.
So the first one was ionic bond?
Right. The first one was ionic bond, and it turns out. I'll just draw this. Here's my quick little periodic table. Here's my quick little periodic table, and it turns out that ionic bonds happen mostly. Okay, well here's our noble gases. They don't do anything. Ionic bonds happen mostly between things in this column and things in these two columns, with some that also come from the next column. So basically column 7, some from column 6, and always with these other things. So everybody else, for the most part, this isn't 100% true because the transition metals can also form ionic compounds. But let's not overthink this. Everybody else, like for example, okay, I made this too small, but group 5 and group 4. Okay, I really blew this. Here's another one over here. But like carbon is a big one for the covalent compounds. There's a number of them that are going to form not ionic compounds because they're not electronegative enough. Why, hello. Go on and just don't kick the camera on your way in.
Move it.
Nicely done. Nicely done. Thank you. It was like the limbo. Okay. But anyway, so like these are the ones. Think of it like this. Some elements have enough power to pull away electrons. Some have to share, and that's really the point. So if you're not strong enough to pull them away, most people end up sharing. Covalent bonding. And I'll tell you, I'll really get into what the roots and prefix mean in this. So here's oxygen. I'm only going to draw the outer shell, the valence electrons, right? And here's oxygen with its 1, 2, 3, 4, 5, 6, right? S2P4. It's 6 outer electrons, and it needs 2 more. And here comes hydrogen. And here's hydrogen's 1 electron. Of course, how many does hydrogen want to have? 2. And here's another hydrogen. And what happens instead, because neither one is strong enough to pull the electron away, certainly not hydrogen and not even oxygen, then they end up sharing. And the way that works is that, and this is the simplified version. So okay, guys, back to the chemistry. Here's hydrogen. Here's its electron, which is I've drawn the electrons different colors, not because they're different. They're not. They're exactly the same, but just to show whose is whose. And so normally hydrogen's just there, and its electrons going around. It's actually going around in a sphere, but since I couldn't draw a sphere to save my life, we'll just do a little ring here. But once a covalent bond is formed, it starts to go sort of around the whole thing. And this is way oversimplified. It doesn't really go around the whole thing like this, but it sort of does.
That's why your markers die.
I know, I could do this. Sometimes I just do this by myself. I find this really soothing. It's kind of hypnotic, right? But so there goes. So in other words, the electron here effectively is also, don't forget, 1, 2, 3, 4, 5, 6. Here's oxygen 6, and so this electron effectively becomes an electron that oxygen has too, as does this one over here. And so everybody's happy because with these two, oxygen now has 8. So it's sharing, but it's good enough. So having it most of the time or half the time is good enough for this atom to feel satisfied with its lot in life. And then also the electrons from oxygen are also shared. And again, this is way oversimplified. This electron doesn't really get shared through the whole thing, but I'll tell you more specifically what it looks like in a minute. But the point is, this becomes part of now what we call a great big happy molecule. So finally, we've been in chemistry like, this is the 9th week. We finally get to use the word molecule. Up until then it was only ionic compounds, which are known as formula units. This is a molecule, which is a group of covalently bonded atoms. Again, the octet is satisfied because everybody has 8. 1, 2, 3, 4, 5, 6. Whoa. 1, 2, 3, 4, 5, 6, 7, 8. Atoms. 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 Is that what's bonding?
There's only one hydrogen.
Oh my god. Alright. Here's oxygen. I'm going to write OX so you don't think this is a little circle, because previously we've done the S and P orbitals like this, right? The S and then the 3P orbitals. We're going to change that a little bit because the book uses a slightly different motif, and since you need to be studying from the book, I'm going to use their motif now. Here's an S, and here's your 3P orbitals, right? This would be your PX, PY, PZ, and here's your S. Yes? Okay. Now, again, oxygen is S2P4, and so that's 1, 2 in the S, and then 1, 2, 3, 4. Otherwise known as this in the Lewis dot diagram. Here's your S electrons, here's this, and I'll do it like this, for the heck of it. Alright, so what happens when we have a covalent bond, the way that you need to think about this is, it's much more specific than this. This is just the general idea. Here's hydrogen. Hydrogen. Here's hydrogen. And it looks like this, right? Because, hydrogen is just 1s1. And so here it is, and here's hydrogen's Lewis dot diagram. Is that hydrogen is going to pull up here, and it's going to share. And here's the other hydrogen. It's going to pull up here, and it's going to share.
Wait, there's 2 hydrogens?
Well, right. Remember, that's what we had before. Remember, we had oxygen with the 2 hydrogens attached to it. And so what we're actually seeing, folks, here, I know that we've been getting off task a little bit, and I know I just spoke in Spanish about maybe taking the test a different day, but and got everybody.
Were you serious about that?
Yeah.
Sí.
Por supuesto. But
What did you say?
let's talk about that later, okay? I don't want any record of me being reasonable. Okay. What's going on here, folks? You have to understand. This is hydrogen number 1. This is hydrogen number 2. So, let's call this one number 1. This one number 2. So, what's really happening is this is the shared electrons. So, what's really happening is that they're sharing between the empty orbital on the oxygen and the hydrogen, both of which need 1 to be full, right? Notice how the full ones don't interact at all. The ones that already have 2, they don't interact. It's the ones that have only one that interact. And here's hydrogen number 2, which bonds by sharing between the 2 orbitals. So it really shows how what they're actually doing isn't just, it's, yes, they're filling the octet, but they're filling it by sharing between half-full orbitals. And if you want to look at it like a Lewis dot diagram, here, we'll make hydrogen blue so that there's a little bit of contrast. It looks kind of like this. So once again, like this is this full orbital from oxygen, which isn't participating, and then this is the other full orbital from oxygen, which isn't participating. This is the half-full orbital from oxygen sharing with the half-full oxygen from hydrogen, and this is the other one. And so what this Lewis dot diagram of a compound is now showing is the sharing that's going on. See?
Oh, so it's sharing so it makes a full equilibrium.
That's right, full octet. And then, so what you want to do to make sure that it's done correctly is you want to count the electrons. 1, 2, 3, 4, 5, 6, 7, 8. Everybody's happy. Hydrogen has 2, which is all hydrogen needs. Oxygen has 8. Everybody's happy. Half-full orbitals are now effectively full. So think about that for a second while I prepare this side of the board for the next example. Does anybody have any questions about that? Oh, by the way, wait. Back to what I promised, which was that we would just explain what this means. So bonding, I think we understand. Bonding is bonding. But covalent. So what's really going on with covalent bonding? Co, together, and valent, meaning the outer electrons. I don't know the Greek root or whatever. I'm just saying covalent. They share their valence electrons, so that everybody can be happy.
Valence?
Yeah, valence electrons are your outer electrons.
Sorry if I'm not smart.
Nitrogen is S2P3, right? And if you look at nitrogen over there, it's in group 5. It's, let's do this too. If we were to look at nitrogen, it has a full s orbital and then 3 half-full p orbitals.
Found it yet?
Are you talking to me?
No, I was talking
Okay.
about those numbers.
And all right, I'm going to do. Here's the. Here's the S and the P. Here's the full s orbital. Here's the 3 half-full p orbitals. Can you already hopefully start to see where this is going? Why we have 3 hydrogens in NH3?
Yep.
It's because there's 3 half-full orbitals, and so when hydrogen, which is still that, color coding, still that, hydrogen comes along, it's going to, here's hydrogen number 1, hydrogen number 2, hydrogen number 3. Each of these brings an electron to the party, and so they're all going to be able to share. So there's sharing between these two. So if we draw, there's a lot of ways to draw this. Here's one. That's another way to do this. And so like this is a stick, like a ball and stick figure, I guess it's called. And what this really represents is the 2 shared electrons. And so like this would be this bond, and this line would represent this bond, this line would represent this bond. And so that's your three hydrogens, each of which is sharing 1 electron. And I'm gonna actually I'll also show you the Lewis dot diagram, which looks like this. And I want to show you one more thing, just to make sure people are down with what I'm talking about. Are you down? Word. Okay. Also on tape saying that. Let's let me try to draw one more thing, and then I'll back up for a second and let you collect your thoughts. So here's the 2s and 2p orbitals of nitrogen, right? Just to review, we have our s electrons. I'll do them in red, which we know aren't going to really participate. I just kind of want to put them so they'll be out of the way. Here's the here's a p orbital. Here's the p orbital in the y-axis. Here's the p orbital in the x-axis. And here's the p orbital in the z-axis. This is the last sort of new wrinkle on this. And so if we draw the nitrogen as it is beforehand, before it bonds.
It's going to have one in each of those orbitals.
Yes, exactly. It's going to have one in each. So, like, here's one on the x-axis. We can say that's this one. Here's one on the y-axis. And here's one, whoops, see, that was a mistake. Here's one on the z-axis, right? So 1, 2, 3, 4, 5, but specifically one in each orbital, and then you have the two that aren't going to interact at all because that's the full s orbital. So what the hydrogens actually do is they come here, here, and here, each bringing their electrons. And so that's what's actually happening. It's a little more complicated than the Mickey Mouse thing I drew before. But
Hey.
nice. Hey, we're taping here.
Sorry, Mr. Arbach.
Thanks, Alyssa.
I didn't mean to.
Like, I didn't know who it was.
All right. So there's like let's say that's this one. So that's the shared. So there's really only two shared electrons per orbital. And here's this one. Oops, going around. I have a harder time drawing this. And here's this one. But the point is that everybody's sharing electrons, and it's really a wonderful, happy little world we have here, even though it stinks because it's ammonia. All right. Are there any questions about that? Let's put I'll put our Lewis dot diagram back. Okay. All right. So, yes.
Why do they use the s orbital and p orbital and d and f and why do they pick those letters?
Physicists, and physicists are kind of like tech people. It's like you ask them a question, and any specialist like gives things in a way that makes sense to them, and not a way that's going to make sense to the common person. So if they thought this through and say, okay, for the next 120 years, regular people are going to have to learn this. Let's come up with a way that regular people could understand. No. They're like, we're going to call this one the S orbital. There's reasons behind all of them, but they just, it's geek reasons, geek reasoning, which is fine. It makes sense once you understand it, but, unfortunately, I'm your interface between this world and this world, and so I'm sorry is all I can say. What I want to show you is two more types of things because this is important. What we've been looking at are called single bonds because we're sharing one electron each per orbital, per atom. What we're going to see now is a double bond, which often happens between elements. Like, for example, O2, or between what we call diatomic ions, diatomic molecules. God. Oxygen, again, is S2P4. This really won't take that much longer, folks, like maybe 3 or 4 more minutes. Here's oxygen, S2P4, as we've already looked at. There's that, and then there's that, and then there's these. So, okay, O2 is a compound between two oxygens. And I'll do the other oxygen in blue. This is oxygen number 2, which is also S2P4.
S2P4.
And once again, the full orbitals are not going to interact. What's going to interact, though, is these two, let's call it PY and PZ orbitals, just for the heck of it. We'll say this is PX. which isn't going to do anything. But instead of just sharing one, like this is one hydrogen atom, this is another one, this is another one. Instead now, we're going to have 2 electrons shared between these 2 oxygens. And this is called a double bond because 2 electrons are getting shared from each atom. And the way you draw this, first of all, here's the Lewis dot diagram. Instead of just having 1, it's going to be 2. So it would get drawn like this with 4 electrons in between. And then the other way we could draw it is to draw it. Wait, I'm not going to do it right next to it. That's too confusing. I'll do it up here. O2. So instead of having 1 line in between, we would have. Do this. We have 2, and that's representing the 2 shared electrons. And
What are we more likely to see, the Lewis dot?
you're going to see all of them. They're equally likely. On a test, do you mean like between this and this? Which are you more likely to see?
The
Or
one
this?
with that top one.
You'll see them all in different contexts. They're used for different reasons, I think.
So would there be like
So it's still a covalent
Wait.
bond.
Hold on. Lisa asked the question first. So.
would there be a triple bonding?
There is. That's what I'm about to show you. This will be the very, very, very last thing. Very, 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 very. N2. All gases, basically, on the periodic table exist as diatomic molecules. In fact, there's a, it's not an acronym, but a little mnemonic device, which is, I brought Claire home on Friday night. Iodine, bromine, chlorine, hydrogen, oxygen, fluorine, and nitrogen. That's all the diatomic elements. You don't have to know that. You don't have to have that in your notes. Just know that I brought Claire home on Friday night. Don't tell my wife. Anyway, okay, here's nitrogen. Nitrogen is, as you can see, S2P3, as we've discussed, looks like this. S2. And so, P3. And so what happens is, when we have nitrogen number 2, same thing. These 2 aren't going to interact, the 2 s orbitals aren't going to interact, but the 3 p orbitals are going to interact. Each of them is going to be sharing an electron, and this forms a triple bond, which would be written like this, or like this. Okay, so anyway, single bond, double bond, triple bond.
Gold
And
bond.
that
Wait,
is,
so what's the element that's in the blue?
it's the other nitrogen. So this is like nitrogen number 1, this is nitrogen number 2. So it's a diatomic molecule between 2 nitrogen atoms. Does that make sense?
Yeah.
Okay, do this all day. Let's go. You ready? Go.
5 minutes of sleep in the class.
1, 2, 3, chemistry! Okay, anyway. Alright guys, I know, that's pathetic. Okay, thank you very much for your attention.